If you want low latency and low cost without sacrificing quality, you need routing, not vibes. We'll build a fast-first router and escalate only when signals say it's necessary. You have a model budget and a speed target. Your users want correct answers fast, and you do not want to call the expensive model for every query. By the end, you will understand a simple Python router pattern that sends cheap answers first, scores them, and only calls the expensive model when needed. You will also see how to measure the trade-offs in both time and dollars. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Think of the problem like triage. Incoming user questions arrive at a steady pace. A heavyweight model gives great answers but costs time and money. A lightweight heuristic is cheap and instant, but brittle. The router decides which model answers each question, so you get the best mix of speed, cost, and quality. At a systems level, the router solves a common production pain point. Success looks like most queries answered by the cheap path. Only a minority escalated to the smart model, and clear metrics for latency and spend. A realistic downside is that a keyword heuristic can miss rephrased queries. That is why we pair it with a confidence signal and a threshold to control escalation. The core idea is simple. Fast first means try a cheap function that often solves easy cases. Smart second means run the expensive model only when the cheap function is not confident. We will show a tiny corpus, one toy query, and a threshold that decides whether to escalate. This makes the pattern visible and testable on your laptop before you scale it. We will build 5 focus snippets. Each one adds one concern: a cheap rule, a confidence score, routing logic, resource accounting, and a safety guardrail. These pieces stack to a production-friendly router that you can adapt to your own models and budgets. Now we'll show the basic, cheap heuristic in action. This snippet shows a fast, cheap heuristic model answering a simple query. The variable q holds a tiny question. The function fast is a lightweight rule that checks whether the word France appears, and if it does, returns Paris. Otherwise, it returns IDK. There is no randomness, so the result is deterministic and instantly reproducible. The point is to mimic a low-latency, low-cost first pass that relies on a single keyword match. The output demonstrates how a bare minimum heuristic can be extremely quick and stable, yet fragile when the user phrases the question differently. Next, we'll attach a simple quality signal to the fast result. This snippet adds a confidence score to the fast model's answer. The variable q is the same tiny query. The function fast now returns a tuple of text and confidence, where a keyword hit yields Paris with confidence 0.6, and a no-hit yields IDK with confidence 0.0. The code rounds the confidence to 2 decimals for readable output. Returning both answer and confidence gives later routing logic a numeric quality signal it can inspect to decide whether to accept the cheap result or escalate. Treat confidence like a quick heuristic estimate of answer reliability. Now we'll implement routing based on that confidence number. This snippet routes by confidence, escalating from fast to smart when needed. The variable q is evaluated by fast producing an answer and a confidence. The variable t is a threshold. If confidence is below t, the code calls smart to get a higher quality result. The variable a holds the final answer and c the final confidence after any fallback. Increasing t triggers more smart calls, which improves average quality at the expense of higher cost and higher latency. Decreasing t does the opposite. The printed tuple confirms which model supplied the final output and what confidence we associate with it. Next, we'll make the resource cost explicit so decisions are measurable. This snippet tracks latency and dollars when the router escalates. The variables ms and cost capture the fast model's 20 milliseconds and 10 cents. A Boolean need checks confidence against the threshold t, and if true, we switch to the smarter model and add its 120 milliseconds and $1.20. The variables add_ms and add_cost represent the extra budget consumed only on fallback, and the code sums totals to make latency and spend explicit. This mirrors production billing and timing, so you can see how raising the threshold will increase total latency and cost in predictable ways. Finally, we'll add a safety guardrail for risky queries. This snippet adds a safety guardrail that forces escalation on risky content. The variable risky lists keywords that should bypass the fast model regardless of confidence. The variable need becomes true if confidence is below the threshold or a risky term appears, pushing the query to smart. The totals mesnt cost include the fast pass plus any fallback cost, mirroring how a monitor would record real resource usage. Expanding the risky set proactively moves more queries to the smart model for safety, while increasing the threshold makes escalation more frequent generally. Recap: it is a fast first, smart second routing pattern that balances latency, cost, and quality. Use it when many queries are simple and a cheap heuristic can resolve a large fraction quickly. Caveat: cheap heuristics can be brittle, so measure failures and tune your threshold and safety rules. Next step: tune the threshold T and run timing and cost experiments on a larger corpus. Or swap the cheap rule for a small embedding model and compare trade-offs. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.